You know that specific frustration of trying to cook with a stainless steel pan?
Oh, yeah. It's an art form.
Right. I was trying to get fancy the other night, reading all the instructions about, heating it up just right. And I flicked some water on it to test the temperature.
Let me guess. You wanted that satisfying sizzle.
Exactly. I expected a sizzle, but instead, the water just beat it up into these perfect little spheres and started racing around the pan.
Like tiny hovercrafts.
Yes! I honestly just stopped cooking and watched them glide.
Yeah, you stumbled right into a classic physics demonstration there.
I did.
Yeah. That behavior is the Leidenfrost effect. It's actually named after Johann Gottlob Leidenfrost. He described it way back in 1756.
Wow.
It was one of those moments where kitchen physics feels, a bit like magic.
It really does. It effectively turns the pan into an air hockey table for water.
That is a perfect analogy.
But what's wild to me is the counterintuitive nature of it. Logic says a hotter pan should boil water faster.
Right, but
But once you cross this threshold, I think it's called the Leidenfrost point.
yes, which is around 193 degrees Celsius or about 380 Fahrenheit for water,
Right. The boiling process actually slows down dramatically at that point.
because it creates a thermal bottleneck. See, below that temperature, water touches the metal directly. Heat transfers efficiently and it just boils away.
Makes sense.
But above that threshold, the bottom of the droplet vaporizes so instantly upon contact that the vapor can't escape.
And that flash of vapor just gets trapped underneath the liquid.
Exactly. It forms a gas cushion.
So the drop is actually levitating.
Basically, yes. It's roughly 0.1 millimeters thick. The droplet never physically touches the hot pan again.
Which is why it survives so long.
Yeah, that separation is key. Gas is a terrible conductor of heat compared to liquid or metal.
So acts as an insulator.
A powerful insulator. You are blasting the pan with heat, but you've built a shield, preventing that heat from reaching the rest of the drop.
You essentially create a frictionless environment using nothing but temperature, which is incredible.
Yeah.
And speaking of removing friction, that brings us perfectly to our sponsor today, Silk. Because if you are trying to integrate AI into your business, you know the process usually has a lot of drag.
Definitely. Whether it's training, automation, or software development.
Right. And Silk acts as the integration layer to smooth all that out. They help you uncover exactly where AI agents will make the most impact for your business or your personal life.
You can check them out at embersilk.com to remove the friction from your AI strategy.
Now, getting back to the physics here, this hovercraft phenomenon isn't limited to just water on a hot stove, is it?
Not at all.
I was reading about the inverse Leidenfrost effect, which basically flips the script entirely.
Right. So instead of a cold liquid on a hot solid, you have a relatively warm liquid dropping onto a super cold bath.
Like dropping room temperature liquid onto liquid nitrogen.
Precisely. The nitrogen boils instantly beneath the drop.
So the droplet skittering across the surface isn't floating on its own steam.
No, it's floating on the nitrogen gas boiling off the surface below it.
That is fascinating.
And it gets weirder. In 2015, researchers found the reactive Leidenfrost effect.
Okay, what is that?
They discovered they could make solid materials hover on hot surfaces too. Things like cellulose or wood.
Wait, wood doesn't boil?
No, but at extreme heat, around 750 degrees Celsius, it undergoes pyrolysis
Oh, so it decomposes.
rapidly, releasing gases from the bottom. That outgassing provides the exact same lift as the steam does for water.
That gas barrier concept actually explains that terrifying Mythbusters finale.
Oh, the molten lead demonstration.
Yeah. The one where they dipped a wet hand into molten lead.
A very high-stakes demonstration, yes. The moisture on the skin vaporizes instantly. It creates a temporary steam glove that insulates the flesh from the 800-degree lead.
Just for a fraction of a second.
But it works.
Please, nobody listening should try that at home.
Absolutely do not.
But scientists are using this for much safer, high-tech applications now, like in mass spectrometry.
It's a brilliant use case. If you need to analyze a tiny chemical sample, putting it in a normal container risks contamination from the walls of the vial.
Because it physically touches the glass or plastic.
Right. But by using the Leidenfrost effect, they can levitate the sample droplet.
So it remains 100% pure while the heat slowly evaporates the excess liquid.
Exactly. Concentrating the molecules for analysis.
It's just so clever. Using a physical anomaly to solve a contamination problem?
There are even prototypes for sublimation heat engines now.
Really?
Yeah. If you can sustain that vapor layer, you have a moving part with virtually zero friction. It opens up amazing possibilities for efficiency in future machinery.
That really makes you optimistic about what's possible when we master these fluid dynamics. There's so much potential to build better, cleaner systems.
Incredible potential.
Well, that is it for this deep dive. If you enjoyed our conversation, please subscribe to this show.
And hey, leave us a 5-star review if you can. It really does help get the word out.
Thanks for tuning in.
Yes, thank you. And here is a thought to leave you with. If we can turn water into a frictionless hovercraft just by adding heat, what other everyday inefficiencies could we solve simply by changing the state of matter we work with?